Good morning. I am Ines Pinkrayem, a PhD graduate student in IT and telecommunication at the University of Toulouse Jean Jaurès. I will be presenting our paper entitled Human Interpretable Rules for Anomaly Detection in Time Series. To introduce the context of our paper, I would like to present this example of cats and ask you the following question. Actually, what's the difference between all these cats? As you can see, the majority represent normal cats, but sometimes you can find differences, for example, in size or behavior with the cat or with the color. So this type of unusual change represents anomalies. So let's consider the following figure, which is an example of time series that contains different types of anomalies. So as you can see, there are 4 types of anomalies, such as peaks, positive or negative peaks, level shift, noise, or constant. So these types of unusual change represent a special case which is essential to detect and must be accurately detected. So we define a time series as a set of observations collected sequentially over time. And in our work, we deal with univariate time series and we define anomalies as observations that do not conform to the expected behavior. In a real context and in our thesis, the experts use their knowledge and manually detect the anomalies. However, with time and the volume of data, experts can no longer understand or detect anomalies. So we need a solution to detect automatically the anomalies. Our objective are therefore to first detect different types of anomalies and second, to produce rules that are interpretable by experts. Having said all of that, we will move on to give an overview of the state of the art. Depending on the need, whether the field of application or the data to be processed, we can use different anomaly detection techniques, such as techniques based on classification, statistic, regression, pattern mining, and so on. So using these techniques, several works on time series have been proposed to detect one or more anomalies as shown in this table. So in this table show an overview of rule-based algorithm, and in general to evaluate the rule generated, there are criteria evoked in this work such as precision or number of rules of the length of rules. However, these criteria cannot be fulfilled all at the same times because if we are looking for a good precision, it's often of the detriment of interpretability. And if we are looking for good interpretability, it's often to the detriment of the precision. So in our work, we're looking for a trade-off between interpretability and precision. We will now move on to our contribution entitled CDT. We will present our method first and then the experiments validation. So our method is made up of 6 steps. First, the time series are pre-processed. Second, we define patterns to automatically create labor time series. Then we create an extension of time series to construct an anomaly detection classifier and to generate decision rules. After that, we simplify the rules and we define a quality measure to evaluate these rules. And finally, we adjust the values of hyperparameters using Bayesian optimization. So we will give an overview of these steps. So let's start by labeling time series. So in time series, we can find different variations between points. And for a given variation, for example, here, a positive peak, different magnitude can't be found. For example, we can have positive peaks with a small deviation around or positive peaks with balanced deviations. So to define this notion of amplitude, we have defined hyperparameters, delta, which is used to distinguish the different magnitude between 2 successive points. So this table presents a formalization of 9 abnormal variations that we have proposed in our paper. and that we use to detect the remarkable points and to label automatically the time series. I will now present our CDT, abbreviation for composition-based decision tree. So we choose decision tree because it represents a white box method, it's interpretable, and it represents a good classifier. So the construction of our process, we need to prepare the input to our decision tree, which is in the form of fixed size sliding windows created from the label time series. So the window system is managed by a hyperparameter omega, which will be automatically defined with Bayesian optimization. After that, each observation or window is associated with a class, which can be 0 for normal or 1 for anomaly. So the root node of our tree represents all the observations. So the idea of our tree is to find a composition which represents a series of remarkable points to optimize separations into two subsets or subtrees. So one which contains the composition and the other which does not contain them. And to find what is the best composition that best separates all the observation, we use an information gain criteria, which is based on the Gini index. Once the tree is built, we can now convert it to a set of decision rules, and to generate rules, the compositions are concatenated from the root node to the leaves. So for example, here from this tree, we can generate 3 rule predicates to detect anomaly. And after that, we can make a simplification, actually a Boolean simplification to eliminate any redundancy. For the automatic selection and quality measure, the last steps, we use the Bayesian optimization to find the best values of our hyperparameter and to maximize an objective function that we define. So as we mentioned earlier, we're looking for a trade-off between the interpretability of the rules and the precision of rules for rules. So for this reason, we have defined a quality measure Q to calculate the interpretability of the rules. And we have the objective function, which is the trade-off between interpretability and the F measure. So we will now move on to the experiments section. We have evaluated CDT using a real data set from the Management and Operation Department. This data represent calorie and electricity sensor data. And also we evaluate CDT using Yahoo benchmark dataset, which represent the actual production traffic of web service. So this table represents the competitor that we used to evaluate CDT. We use F measure, the quality for the interpretability and the objective function for the trade-off. So the following table shows the results obtained. We can see that our method is better as the others with an average improvement between 4 to 20%. We get a good quality on average, and finally, we get best trade-off between F measure and the quality or the interpretability of rules. So I would like to end this presentation by talking about the main points and our outlooks. So we present a method, a pattern-based method to detect different types of anomalies. This method allows to generate few rules of a good quality. And as a perspective, we would make CDT multi-class and we would apply, would like to apply this approach on multivariate time series. Thank you for your attention.